Hello and welcome back to Calculus 1 Saturday edition. So, L'Hopital's rule. Well, not really L'Hopital's rule, it's actually Bernoulli's rule. L'Hopital was a rich guy who liked to learn, and Bernoulli was his tutor. At those good old times, the only way to learn math is to have someone teach it to you. Textbooks did not exist. Books on calculus did not exist. YouTube, believe it or not, did not exist. The only way for you or Google to learn calculus was to find one of 6 people that knew calculus and then, right, pay them to teach you privately. Calculus was not taught in schools, so talk about academic inflation, right? Everyone learns calculus today. Just 200 years ago, only very selected few knew it. So what we do is, so what happened was L'Hopital was not purchasing papers, but paying Bernoulli for tutoring, and Bernoulli was sending papers. So in one of the papers was this rule, and L'Hopital learned the rule. Now, Bernoulli never published the rule anywhere, because they were publishing papers, but there were no books or anything like that. So L'Hopital learned the rule, and no one knew that it was actually something that he learned from Bernoulli, and Bernoulli was the one who invented it. So what happened was L'Hopital writes the first ever calculus book, and that rule was included in the book, and no one ever seen that rule before, and they all thought it was L'Hopital's rule, and it was named L'Hopital's rule because, right? So through the time, all right, it was surfaced that it was Bernoulli, but to still honor L'Hopital for writing first ever calculus book, they never removed the name, so it stayed as L'Hopital's rule, even though it's not L'Hopital's rule. So that's a little story that I like to tell about this, which is interesting. And now, what is L'Hopital's rule? It's a way to take limits. If you remember the good old times when we did the derivatives of trigonometric functions, we covered a specific limit which said that the limit, I don't need to be dramatic, there you go, limit x goes to 0 of sine x over x is equal to 1. Why? How? I just said, remember this, we need to use it now to do the proof, and then eventually I will show you the way. Well, eventually is finally here. Today we'll learn the way to deal with these types of limits. So what is the issue here? Why we can't do it with our old methods? But our old methods were either you look at the graph, which obviously you can always do, or you can look at the chart, which you can obviously always do. But what you can't always do is plug values in and then compute. In this case, you add 0 divided by 0. And that's something that you can't compute. So this rule is specifically designed to take care of those types of situations. When you have what we call indeterminate form, which is either 0 over 0 or infinity over infinity, this is when L'Hopital rule kicks in. And the rule simply says, take the derivative of numerator separately from the derivative of denominator. So you're taking 2 separate derivatives, and the resulting problem will have the same answer, but hopefully it will be easier to compute. So, for the L'Hopital rule, this is what we have. If when x equals a is subbed into the function, we have if we get 0 over 0 or infinity over infinity indeterminate forms, then, and here's what we're doing, limit x goes to a of f of x divided by g of x will have the same answer as limit x goes to a of f prime of x divided by g prime of x. And I'll just box this, and let's go blue. Not a quotient rule. It's two separate derivatives from each other. So what we are doing here is we are taking separate derivatives. Now note the notation for L'Hopital rule that happened. You put L apostrophe H on the equal sign because, guys, functions on the left and functions on the right are not the same, right? The overall function. And here is the first example, immediately the one with the sign we had. Limit x goes to 0 of sine x over x. So this is 0 over 0 when you plug in 0. Sine of 0 is 0, and then you plug in x equals 0, you get 0, right? So now, by L'Hopital's rule, when you take limit x goes to 0, take the derivatives. Derivative of sine is cosine x, and derivative of x on the bottom is 1. So you can clearly see that this function here is not the same as a cosine, right? There is no identity that says cosine is sine over x. No. So these are completely different functions now, but what is guaranteed by the L'Hopital rule and the theorem is that the result they give, the answer that the limit gives, is the same limit. So now when you plug in 0, you get cosine of 0, which is 1. 1 divided by 1 is 1, which is what we were looking for. So this is the way these limits work. If you get 0 over 0, or you get infinity over infinity, you will be able to calculate the limit. Limit x goes to 0 of e to the x minus 1 divided by x. Again, if you plug in your zeros, e to the x is 1, 1 minus 1 is 0, and then you plug in 0 on the bottom, you have this. And then you take the independent derivatives because you have L'Hopital rule. Satisfied, right? And you have now e to the x divided by 1. And now when you plug in 0, you get 1 over 1 equals 1 again. Do you always get 1? No. There will be some examples, infinitely many examples, when you're not going to get 1. Let's see. Limit x goes to, let's say, 1 of x cubed plus x squared minus 2x divided by x minus 1. So you look at this, you plug in your 1, you get 1 plus 1 is 2, minus 2 is 0 on top. in the numerator, right? And then 1 minus 1 in the denominator is also 0. So now, time to take L'Hopital. What I say, unleash L'Hopital upon the problem. And the derivatives, you get 3x squared plus 2x divided by 1. Oh, minus 2 on top. Oops. Minus 2. There we go. Now, when you plug in the value of 1, you can just compute it. You get 3. Right? Because 1 squared is 1, so 3 plus 2 is 5, minus 2 is 3, so divided by 1 is 3. So there we go. Perfect. Let's see if we can find something a little bit spicier on the derivative. Perfect. Limit x goes to 0 of square root of 9 plus 3x minus 3 divided by x. So this is a bit spicier on the derivative because now we have square root. When you check 0, 3x will be 3 times 0. So square root of 9 is 3. 3 minus 3 is 0. So we have a 0 in the numerator. And then we plug 0 for x, which is 0. And it's 0 over 0, so we can use L'Hopital rule. We go and send x equal to 0. And now we need to take the derivative. Now, minus 3, that's going to go away. Denominator is just 1, so that's easy on the derivative. I need to take the derivative of this square root, and that's going to be 1 divided by 2 times square root of 9 plus 3x, and then I have to multiply by the derivative of the inside, which in this case is 3. So now, when you plug in 0, it quickly works out to be a half, because, right, 3x becomes 0, square root of 9 is 3, 3 and 3 cancel, so it's just 1/2 divided by 1, which is 1/2. So we got this result fast as well. Now, before we move to interesting cases, let's take a look at one of your good old limits from chapter 2 that involved asymptotes. So 3x squared plus 2x minus 6 divided by 4x squared plus 1. So something like this in your calculation for asymptotes, you guys learned that you should just, if they have the same front coefficients, you should just take front coefficients if they have the same exponents. That's what I meant. So both have square and a square, so your horizontal asymptote would be 3/4, which means that this limit is 3/4, because limit go to infinity is the one that computes horizontal asymptotes. But now, when you plug these infinities, you get infinity divided by infinity. And if you have infinity divided by infinity, it's a L'Hopital rule. And if it's a L'Hopital rule, you can, if it's in determinate form, you can use L'Hopital rule to solve the problem. So, this will be, take the derivatives now, and what we get up there is 6x plus 2 divided by 8x. Okay. When you plug infinity now, you get infinity over infinity again. You treat this as a new problem and you do L'Hopital again. Exactly. So sometimes you will have to apply L'Hopital rule few times before you are actually able to compute the problem just by plugging in. So now when I apply L'Hopital rule, I will have 6 over 8. Now limit has nothing to apply to, so the answer is just 3/4. So this is the way to deal with these limits. So L'Hopital's rule is applied to a problem when you have 0 over 0 or infinity over infinity. And it's straightforward. Just take independent derivatives and the resulting problem will have the same answer as the original problem. And if you are not getting 0 over 0 or infinity over infinity, L'Hopital rule doesn't apply. You have to use something else. Now remember, your graphs and charts and all of these, right, can always be used. So now that we know the basic L'Hopital rule, we have 0 times infinity case. So we are going to cover 5 special cases that can be converted into indeterminate form 0 over 0 or infinity over infinity. So we have a case now that you plug in your number, whether it's 1 or whatever, x goes to something, x goes to whatever it goes. When you plug that in, you get 0 times infinity. So now we're going to use this special mathematical, this is just algebraic manipulation, right? Which says that you can take function f of x and you can write it as 1 over f of x. So this is the trick that we are going to use. This is just mathematical, like an algebraic manipulation. We are not learning any calculus on this example. All we're going to do is to use this trick to transform the problem into L'Hopital problem, and then just L'Hopital takes over. So let's take a look at an example. I believe that the book starts with diabolical example right away instead of actually giving you something civil to start with. Yeah, the book in... Yep. So let's go into exercises and try to find something that it's civil. I said something civil. They don't have anything civil over here that we can just learn on and then do the example. I guess we'll have to use x cosecant x. Limit x goes to 0 of x cosecant x. So what you have here, well, I'm not going to get to use this, which is bad. We'll use the next example. So this one is just basic algebraic problem. This is 0 times infinity, because cosecant is infinite at 0, positive infinity. So the way to solve this is to change cosecant into 1 over cosine, and you get x over cosine x. And now when you try to plug in your 0, oh my God, sine x. Sine x, not cosine x, sine x. There we go. So now when you plug in your 0, you get 0 over 0. So we transformed the problem from 0 times infinity case into 0 divided by 0 case, which is indeterminate form, which means we can unleash L'Hopital. So limit x goes to 0, we get 1 over cosine x, which is 1 over 1, which is 1. All right, next case, next example is limit x goes to infinity, x squared times sine of 1 over 4x squared. There's no reason to run. X goes to infinity, which means that the x squared part is infinity. Now, what is 1 divided by infinity? 1 divided by infinity is? Very good. So, 0, right? So, sine of 0 is 0. So we have infinity times 0. And this is where we are going to use our transformation. I'm going to take this x squared and put that in the denominator as 1 over x squared. So this is where my function f of x, which was x squared, this is over here like f of x times g of x, right? So my f of x that was in the numerator went as 1 big division line and then 1 over f. Do we all see that? So the formula I had written was f equals 1 over f. So it used to be multiplied into sine, now sine multiplies is 1, right? We don't have to write it, so it's gone. And now, if you plug in your infinity, sine of 0 is 0, and 1 over infinity is also 0. So we have 0 over 0, and that's going to give us the excuse for L'Hopital. So take 2 independent derivatives. Derivative of sine is? Very good. Copy the guts. And then you take the derivative of the inside, which is going to be negative 1 quarter x, no, negative 1 over 8, no, 1 half. I don't know, it's something like that. It's and then the denominator, we are taking the derivative of x to the minus 2, that's a negative 2 over x cubed. Yeah, we have 1 quarter times negative 2 over x cubed. So yeah, I was right. Good. All right. So now we have these, and when I plug in value now, first I have to cancel the I cancel the negatives and I cancel the x cubed. So I hope you see you're getting a quarter over here. Because you have 1/2 divided by 2. This whole thing over here, the cosine of 0 is 1. So this cosine goes to 1 in the limit, because cosine of 0, yeah, 1 over infinity is 0, cosine of 0 is 1. And then you have 1 times a half divided by 2. Half divided in a half, right, is quarter. Let me ask a very interesting question. Please look at the screen. How much is 0 times infinity? In this case, 1 quarter, right? Cool, huh? You didn't know that you multiply 0 by infinity and you get a quarter. So, this is why we can't do these calculations without calculus, guys, because this can be anything. If I play with numbers up there, this quarter changes into a different value, right? If I change this 4 into a 7, then the result over here changes. It's still 0 times infinity, right? But the question is, what is it exactly, right? And it's exactly 1/4 in this case. So it's really, really cool. So I'm going to write on the board stuff that we have done so far. So we have 0 over 0 and infinity over infinity. And I'm just going to say use L'Hopital. If you have 0 times infinity or infinity times 0, use f equals 1 over f. And that will transform the problem into a basic L'Hopital, and then you just apply L'Hopital. The next case that you guys are going to run into is infinity minus infinity case. So that's the next one. And this case is more interesting, because now you know that you can only use L'Hopital if you have infinity over infinity or 0 over 0, right? So previous case was multiplication, and you changed it into division, and everything was nice. But now you have a subtraction. How do you go from subtraction into division? Because your goal is to massage this with mathematical, right, whatever manipulations, until you have indeterminate forms so you can use L'Hopital. So how would you go from subtraction into division? Well, the question is now, can you go from subtraction to multiplication somehow? Because you know how to go from multiplication to division. That's easy, right? With a 1 over f thingy. How do you go from subtraction to multiplication? What mathematical concept helps us with that? Starts with an F. To go from subtraction into multiplication. It's not foiling, it's the other F word. Factoring, there we go. So, we have a roadmap for infinity minus infinity. Infinity minus infinity has a roadmap where you use factoring to get it into 0 times infinity, and then you are using 1 over f to go into 0 over 0 or infinity over infinity. So it's a little bit convoluted, but that's the way it is. So what we have is, so let's, I'm gonna put here, so use factoring, then 1 over f, and it will land you to in L'Hopital. So let's take a look at the limit x goes to infinity of x minus the square root of x squared minus 3x, I think. Yeah. So this is my problem. I have infinity minus infinity because when you plug in infinity, right, you get infinity under the square root. Square root of infinity is infinity, so you have infinity minus infinity. So now your job is to factor over this negative sign that is in front of square root. So what do? Well, you first factor out x squared within the root, and then that x squared escapes the root, becomes x, and then you have x to factor, and there you go. So I need to multiply here by x, so I have x squared to cancel, the two factor, right? Does that make sense, the blue x? Limit x goes to infinity, x minus square root of, and now I can factor x squared, and I'm left with 1 minus 3 over x. Do we all see 3 over x over there? So the blue and black x on top is x squared. That one is getting factored. What's left is 3. And the blue x in the bottom, in the denominator. So when I take x squared out, I'm left with 1 minus 3 over x. Now, guys, this is going to happen every time, so you better be comfortable with this. Now this x squared is going to escape the square root, become x in front of the square root, and then we can factor that one finally. So we have x minus x, square root of 1 minus 3 over x. And now finally I can factor out this x in front and have 1 minus square root of 1 minus 3 over x. All of this algebraic work just to get us to infinity times 0. Because 3 over infinity is 0. Square root of 1 is 1, 1 minus 1 is 0. For the parenthesis. So now you have it. And this is where we now, because we have infinity times 0, this is where we use f is equal to 1 over f. There is a much faster way to solve this problem. You plug it into Wolfram Alpha. And it's done in, half a second. Or you can just use all these steps. Welcome to education in the 21st century, right? The building will withstand the wind, don't worry about it. I know for a fact, we went through a number of hurricanes, this is nothing. So, if you want, you can close the windows So, I'm going to ship this x in denominator as 1 over x, and then we're going to use, because we have 0 over 0, we can use L'Hopital. So mathematical manipulation now. 1 minus square root of 1 minus 3 over x is 1 over x. So that x that was in the numerator goes down into the numerator.
Does it matter which term we put at the bottom?
It actually doesn't.
Okay.
But for some functions, it will, because you will not be able to simplify. For instance, the previous example we had with x cosecant, if you remember that one. If you put if you try to use this trick on x to the cosecant and you put x in denominator, it becomes 1 over x. When you take the derivative, it becomes negative 1 over x squared. And you take another derivative, it becomes x cubed and x fourth. So the L'Hopital rule makes it worse, right? So in some cases, when you put the wrong one in the denominator, it will make it worse. This will actually show up again in Calc 2 when you do integration by parts and you choose it wrong, the next round of the problem is worse. So you will notice that the problem is getting worse because stuff is not canceling, right? The reason why we use this trick is when we take the derivatives and hope for the chain rule to kick in and give us some cancellations, the cancellations actually help us solve the problem. Now, when you put the wrong function, so in some cases, it doesn't matter which one goes in the denominator, right? You will be able to solve the problem either way. But in other cases, it does. And you will know it because one of the two things will happen, right? You can't cancel, or number two, it's getting worse. The derivative of 1 over x is 1 over x squared. The derivative of 1 over x squared is, there are minus signs and constants. 1 over x cubed, right? And then 1 over x fourth. So you can, and you know that you can do L'Hopital rule as many times as you want. So you do 6 L'Hopital rules, and now you are 1 over x to the 7th, right? And nothing canceled, and probably your numerator had 16 different. So yeah, again, experience and amount of problems you do, homework and all of that will help. I am at the stage where I can do L'Hopital now because I have 0 over 0. And you can see that in the numerator you have 3 over x, in the denominator you have 1 over x, so as chain rule those cancel. So we're good. Generally, to have trig and to have 1 over x, generally they are bad because when you take derivatives of them, they don't go away. E to the x as well, right? They just stick around. Derivative of e to the x is always e to the x, no matter how many times you differentiate, right? And 1 over x starts picking up the exponent, so it doesn't go away either, right? Polynomials are nice because polynomials diminish with derivatives, right? The rest sticks around. ln becomes 1 over x, becomes 1 over x squared, 1 over x cubed, right? So they're all evil except polynomials. So the derivative of 1 is 0. Oh, I forgot to put the limit. Make sure you don't forget the limits. All right, so what do I have? I copy the negative. Derivative of 1 is 0, so it's gone. The derivative of the square root is always 1 over 2 times 1 over 3, so you copy. And then the derivative of the inside is going to be, copy the negative, and then the derivative of 3 over x is going to be negative 3 over x squared. And then you have negative 1 over x squared here. So now you have a whole bunch of these negative signs floating around. So these cancel, and then these ones cancel, so all of the minus signs are gone. And finally, the x square and x square cancel as well. So what's left? What's left is just 3 over 2 square root of 1 minus 3 over x. That's what's left. Everything else is canceled. Minus signs with minus signs. And then 1 over x squared, 1 over x squared, so it's all gone. Denominator is gone completely. And you are left with 3 over 2 square root of this. So now, when you plug infinity, what's 3 over infinity? 0, right? Square root of 1 is 1, so who would say infinity minus infinity this time around was 3 halves, right? So the answer will depend on what type of functions, right? What kind of constants you have inside the thing. All right, before we go and start, generally you guys don't like these. So before we start, the next one, let's take a look at your math skills. Try tangent minus secant. So limit x goes to pi over 2 of tangent x minus secant x. So try that. I'll be right back. So, what's the deal? What do we do? We switch to sines and cosines. Sine x over cosine x minus 1 over. Yep. And then we just factor. Oops. So now we have 1 minus 1 is 0, cosine of pi over 2 is 0. So we can use L'Hopital's rule to solve this in one step. We have derivative of sine is cosine x divided by negative sine x. So it's 0 divided by negative 1, which is 0. So that's the answer. Cases 1 to infinity, 0 to 0, and infinity to 0. All three cases are solved the same way. Use ln. That ln looks like lu. So ln, there we go. So what do we have? Say you are looking at the limit x goes to infinity of 1 plus 3 over n to the n. So this is our limit that we are supposed to look at. And how do we solve this? So we start with y equals, and then we put some separation here because I need to put in ln. And then I add ln to both sides. This ln will allow us to take that exponent n and put it down. So now what I have is ln y is equal to swap the limit and ln, and the exponent comes down in front of ln. So from here to here, we are using the property that ln x on the p is p ln x. So this is oh, he smelled bad or something?
No, there's chocolate there. I already explained.
No, I'm just kidding. You actually have outlet under the desk, isn't it? All right. Anyway, so I always go with the worst possible scenario. You know that.
I know.
So this is how this n ended up in front of ln. Using that formula, we call it a power rule for logs, right? So now, when I take a look at this, it becomes infinite. Hold on, I'm having n's and x's, and these are all either x's or they're all n's. You can't have x and n. So switching these two n's, that's faster. N. Is there, see, there's n. Okay. There we go. All n's. All n's. Or all x's. Or all t's. Doesn't matter. It has to be the same variable throughout the entire problem. Good. So now, when n goes to infinity, the first one, right, there's a multiplication in between n and ln. So when n goes to infinity, right, that's that one. And when n goes to infinity here, 3 over infinity is 0. So ln of 1 is 0. So we have our infinity times 0. So now, ln y is equal to limit n goes to infinity, and I have to use our trick to put this as 1 over n in denominator. So if we do that, we see that now we have 0 divided by 0, which is where we can use L'Hopital rule. So ln y, and then we put the L'Hopital. We know that we are going to use the derivatives. The bottom is easy, 1 over n squared, so that's done. On the top, you take the function as is, which is 1 plus 3 over n. Put that in the denominator. And then put its derivative in the numerator, which is negative 3 over n squared. So this is a lot now in terms of algebra. But luckily, you guys had those complex double fractions. Now this is, I don't know, sixfold, right? So what do? You have negative 3 over n squared over 1 plus 3 over n. And you have that divided by the denominator, so times negative n squared. So now that negative n squared will cancel the denominator. Here. And the negatives will cancel. So now you are at ln y is equal to the limit n goes to infinity. And you are left with 3 divided by 1 plus 3 over n. So when you get infinity, you just get 3. So ln y is 3. You just want to get y alone, so e both sides, and you get that y is equal to e cubed. Now y was your entire limit from before, so limit n goes to infinity of 1 plus 1 over n, no, 3 over n raised to the n is e cubed. That's the answer. That's the answer. And I hope you see that this answer is giving you the definition for e. Right? So now we can actually write the formula that the limit n goes to infinity of 1 plus r over n to the n is equal to e to the r. That's actually a formula that will be very useful for your Calc 2, so you don't have to solve these limits all the time. They pop up, Calc 2. So if that r is 1, so you have 1 plus 1 over n, then it's just e. And that's a definition for e by Euler. Yeah. So 250 years old. It's nice. All of those cases, 1 to infinity, 0 to 0, and infinity to 0 are solved the same way. Try this one. Limit x goes to 0 of tangent x raised to the sine x. You were familiar with tangent squared. How about tangent to the sine? And if you're wondering why, because we can. That's why.
So with all of the ladies and the morning, but no, yeah, about tomorrow morning, but we start all the time. You're gonna get it?
Yeah.
They will be. No, if it doesn't rain today, you know, because we're not going to bother you, we're walking on, you know how you have the yellow line on the road? So we're walking along the yellow line, and we go how far the grabber can go onto the grass. We don't go into mud. So even if it's raining, it's still fine. But we don't, yeah, we just don't want. So if it's raining, we'll reschedule for the next Sunday. If it's not raining, yes. So we meet at the park tomorrow here. Number one, yeah. And then we get dispatched by us. Yeah. Well, the reason is no traffic. So that's the whole. So Rutgers is doing their Rutgers Road is doing their thing today. And they have it at like 10:30 or something. If you follow them on Instagram, you know. And, yeah. So they are doing it right now. And I don't like it because it's a lot of time. You know? In the morning, you don't have that many cars pass by, so it's safer. You get the rest, and you know, I get the rest to get a driver or a bag or two in the car, right? So one goes the bag, one goes the driver, and then we see if we collect more alcohol at the end of the day. No idea how many bottles, and especially those small bottles, you find that people drink them.
Here, you can to cheat and win. All right, so same rules over here. We have y equals, then we put ln on both sides. So leave some space, put your tangent x, put your sine x, and then put ln on both sides. So now we have ln y is equal to the limit of x goes to 0. I'll immediately put sine x and then ln of tangent x. So now ln y is the limit x goes to 0 of ln of tangent x divided by 1 over sine x, and that's cosecant x. So when I put 0, ln of 0 is infinity, cosecant of 0 is infinity. So we have infinity over infinity, and we can unleash L'Hopital. So now I have limit x goes to 0, tangent x goes in denominator, and then the derivative of tangent is very good. And then in denominator I have a derivative of cosecant, which is negative cosecant x cotangent x. And now we fix this as much as possible. So we have secant squared x divided by tangent x negative cotangent x cosecant x. Cotangent, so tangent times cotangent, they cancel, because tangent is sine over cosine, cotangent cosine over sine, they just cancel. And secant is 1 over cosine, and cosecant is 1 over sine, so this works out to be, don't forget the limit, negative sine x over cosine squared x. There we go. And when you plug in your 0, you're just going to get a big fat 0, because sine of 0 is 0 and cosine of 0 is 1, so 0 divided by 1 is 0. And you have ln y equals 0. You're not done, because you have to e both sides to get y alone. So y is e to the 0, which is 1, which means that your original limit, which you defined as y, is was tangent x raised to the sine x is actually equal to 1. And you're done. At the end of this lecture, we have something very important that you will update in Calc 2, should you go there, and that is the growth rate of functions. So some functions grow faster than others, and this is simply a ranking of what function grows faster. So to simplify what the book has, the slowest one is ln x. So that's the slowest growth, followed by root of x, followed by polynomials, followed by exponential ones, and finally the boss x to the x. Now they put some exponents around, and they, more particular, but in general, if you are taking derivative limits that go to infinity, you can just take a look at what type of a function you have and make a decision most of the time. To prove to yourselves that these values grow in such way, you can just complete the chart of values. So 1, 2, 3, 4, 5, and 6. So if you are using a linear function, which is 2n, these numbers are just 2, 4, 6, 8, 10, and 12, easy. If you are using polynomial x squared, cheapest one, right? Then you are getting 1, 4, 9, 16, 25, and 36. And you can see that the y values for n squared are growing faster than the y values for 2n. Because at the line 6, 2n is at 12, and this one is at 36, 3 times larger. So, right, there's that. Now, 2 to the n is going to be 2, 4, 8, 16, 32, 64. So, 2 to the n is almost twice as fast at level 6, right? Because like 36 times 2 is 72, but then this is 64, but still, right? So exponential growth is so far the largest one you see. Now that one is nothing compared to our friend n to the n, which is the boss of all bosses here. 1 to the 1 is 1. 2 squared is 2. 3 cubed, right? Because it's n to the n, so both numbers have to be the same. 3 cubed, that's 27. So it already obliterated on the line 3, all others. 4 to the 4, right? So that's 16 squared for 256. The others are stuck at 16 at best. You see that? Now, 5 to the 5, we can just write a lot and be satisfied with that. 5 to the 5, 3,125. And 6 to the 6 is 46,656. The boss, right? Now, what does this mean for our limits? Well, if you are comparing any of these, it's always clear which one is faster, which one is slower, right? So, now, this is not mathematically correct notation, so quote me here. Limit as x goes to infinity of slow over fast is going to be 0, because the denominator is going to shoot to infinity faster than the numerator, so it's just going to pull the limit down into a 0. Another quote, limit x goes to infinity of fast over slow is going to be infinity. The denominator will not be able to make up, right? If you are doing the limit of two functions that are of the kind, so polynomial over polynomial or exponential with exponential in some sense, then you actually have to go and do the limit the way we did. But if you have limit, and this is just to go to infinity, right? If you have the limit and the function in the numerator and denominator are not of the same kind, then one of these rules are going to kick in, and you can just solve the limit without going through L'Hopital, hoops, and everything else. And that's it. Bye.